Hey everybody, and welcome back to the Foundations of Science Common Curriculum class on earthquakes. Today's slideshow is going to be about the basics of plate tectonics, again focusing on what do you need to know about plate tectonics to help you understand earthquakes, the damage they cause, how big they are, and how frequently they will likely occur. Remember last time we talked about how the Earth is structured. In this simple cartoon of the Earth, we see a solid inner core made of iron and nickel alloy. If you hit it with a hammer, it makes a ring. You see a fluid outer core made also of nickel and iron, but it's got a viscosity similar to water, so if you hit it with a hammer, it makes a splash. Instead of the mantle, we're going to be talking about a plastic asthenosphere. You hit it with a hammer, it makes a thud, and floating on top of that plastic asthenosphere is a solid lithosphere. You hit it with a hammer, it makes a crack. That crack is where most earthquakes occur. Recall that these lithospheric plates sitting on top of the surface of the Earth are broken up into individual parts so they can move around on the surface of the Earth. This image shows you the major plates, including North American, Eurasian, Pacific, South American, Indian, etc. You see things get very complicated around Southeast Asia, where it breaks into a series of microplates, but Singapore is located fully on the Eurasian plate. We talked about how different plate boundaries manifest themselves. In the middle of the oceans, we tend to have oceanic spreading ridges where basaltic rock is created. This basaltic rock tends to be more dense than the granitic rock that occurs on continents. Therefore, it sits lower on the surface of the Earth and forms the ocean basins where our oceans occur. The divergent plate boundary in the middle of the oceans is where this crust is created and two plates pull apart, driven by convection. Where the two plates come together, we call that a convergent plate boundary, where subduction zones occur, where usually the denser oceanic crust gets thrust beneath the less dense continental crust. This is where the biggest earthquakes occur. And sometimes, kind of as an accommodation trick for these solid plates floating around on a spherical surface, we have what they call transform plate boundaries, where two plates slide across one another. These plate boundaries are very similar to what they have in California on the famous San Andreas Fault, which we'll be looking at in the Los Angeles section, and on the North Anatolian Fault in Turkey. Spend a little bit of time looking at the surface of the Earth and some of the things we see on the surface that helps us prove plate tectonic theory. This image shows both the bathymetry, or the under the ocean topography. You see the high points there in yellow where the mid-ocean ridges occur, and also topography, where we see mountain ranges and basins and all sorts of things on land. So back when I was a kid, my Granny McAdoo gave me a globe. On this globe, I used to study it when I was maybe 6 years old, and I would look at it and say, wow, it kind of looks like South America could fit right up underneath the Horn of Africa. And came up with a theory for how that must have come apart. I decided there must have been a big comet or a big meteorite that hit the Earth, and it thumped the Earth, and the two continents lifted up and then fell back apart to where they are right now. Well, I wasn't too far off, but rather what seemed somewhat improbable. The plates actually floated apart over the course of, 60 or 100 million years. Back in the Pangea time, about 120 million years ago, I believe, all the continents would have fit together, as you see in the image here, with very little overlaps and gaps in this particular map. Further evidence that the plates were all together at one point is from the fossil record. Different species of the Glossopteris flora match up along similar low-lying latitudes in the southern part of South America, southern Africa, India, which is at a much higher latitude, Australia, and Antarctica, as do fossils of the amphibian Mesosaurus. Showing the continental arrangement back during the Pangea time, similar evidence includes glaciers, and the striations that these glaciers left on solid rock all point to an ice cap that would have been focused right between Africa and Antarctica, pushing out in all directions. This is an image of the mid-Atlantic ridge where it comes above land in Iceland. Geologists often wonder why this happens to be the case. Why is it this more dense basaltic rock is actually above land only at Iceland? And perhaps I'll leave that to an exercise for you to sort out. These mid-ocean ridges, especially near Iceland, prove some of the initial evidence for plate tectonics. Turns out what happens over the course of geologic time is the Earth's magnetic field is recorded in the molten basaltic rocks as they come out of the volcanoes of the mid-ocean ridge. These rocks have small magnetic particles in them. When you draw a magnetometer, something that measures the strength of the magnetic field, over these rocks, the orientation of these small magnetic particles either accentuates or diffuses the signal of the magnetometer. So back in World War II, when they were doing lots of surveys of the seafloor, they were dragging magnetometers over the seafloor for various reasons, looking for heavy metals, evidence of warfare, and this sort of thing. And they noticed the signal fluctuated somewhat regularly, and really interesting, it had a pretty much symmetric pattern perpendicular to the mid-ocean ridge. So it would get stronger than weaker on either side of the ridge. Over the many years and decades, they mapped out most of the world's mid-ocean ridges and found the symmetric pattern on either side of the mid-ocean ridges exists in all the world's oceans, suggesting that in the middle of these ridges were creating crust, and over geologic time, as the polarity of the Earth's magnetic field changes, it actually changes polarity, it flips 180 degrees, it's recorded in the rocks. This is somewhat of a terrifying prospect if you think about it. The Earth's magnetic field can actually change. Sometimes you have a compass and the needle points to the north. You come back a few million years later, and that same north arrow is actually pointing to the geographic south. One thing that keeps me up at night is what happens when those magnetic fields actually flip-flop. This is a computer model that shows the chaos that ensues during a magnetic reversal. Considering the Earth's magnetic field is what's responsible for protecting us from all kinds of radiation from the sun, makes me wonder, what is it like living on Earth during a magnetic reversal? How long do these reversals last, and is there actually any effect on life on Earth because of the protection of the solar field? A lot of animals navigate by magnetic navigation, this sort of thing. Really interesting questions we don't know the answers to. Further evidence of plate tectonics is shown by volcanic chains and hotspots. This is an example from the Hawaii hotspot chain where we have a stable hotspot that doesn't move at all, and the plate actually moves, in this case, to the northwest. The active volcano at the Big Island of Hawaii shows active volcanism and the highest topography, and as you continue on to the northwest, the volcanoes become less active and the topography goes down. Here's an example of a broader view of the Hawaiian chain and the Emperor's Seamount chain. If you look carefully at it, there's a curious dog leg in the chain, which suggests that the plate motion must have changed rather drastically at some point in geologic time. We're not sure exactly why this change took place, but it's clearly recorded here in the chain. This is a picture of Mauna Loa in Hawaii Seamount chain. Notice that it is a very broad, low topography. It's actually pretty high topography, but it's very broad, not very sharp seamount volcano. Turns out that basaltic rock, when melted, is a lot less viscous than continental rock. Continental rock, these granites, when you melt them, tend to be very viscous, so when they get melted, rather than flowing like a river or like lava we think of at the Hawaiian volcanoes, they actually explode and they cause very violent eruptions. One of the most violent eruptions in the history of the Earth occurred in the Yellowstone area of northwestern Wyoming. Turns out there's a hotspot chain that tracks the progression of the North American plate to the southwest. Presently the hotspot is under Yellowstone, melting continental crust. When that eruption happens, and it will happen at some point, it can cause major ashfall throughout most of the North America. This map shows the ashfall both from Mount St. Helens eruption in 1980, very small area, and by comparison shows the ashfall recorded in geologic time 2.1 million years ago, 1.3 million years ago, and most recently just over 500,000 years ago. If this eruption were to happen today, we'd have major disruptions not only in air travel but also in food production, as this eruption would cover most of what we call the breadbasket of the United States. But I digress. This is what we tend to think of volcanoes looking like. This is what we call a stratovolcano where we've got very viscous eruptions. They don't tend to flow, they tend to explode, sending ash like this kilometers into the sky, very hot, dense flows go down the volcano. As you can see, these strings of smoke coming down what they call nuées ardentes, as these hot, molten flows of lava come cascading down the flanks of the volcano at extremely high velocities. This type of volcano tends to occur at subduction zones. And again, this is where the largest earthquakes occur. This diagram shows both an example of a spreading center, a transform fault, and a subduction zone offshore in the Pacific Northwest of the United States of America. Stratovolcanoes like Mount St. Helens are the ones with the steep flanks, very viscous eruptions, and can cause large ash falls over large areas. If you notice here, there's different places where the earthquakes can occur. We have big subduction zone earthquakes that occur close to the trench, and as you go down further on the subducting plate, we can have smaller, sometimes, intraplate earthquakes. I say smaller because they're further away from the surface. The energy shaking may not be quite as hard, but can still have massive energy release. If this is the case, and this is what the theory predicts, we should see evidence for it. Sure enough, if we look at distribution of earthquakes in this region, we see very shallow earthquakes close to the trench. As we get deeper, the yellow dots represent earthquakes that occur between 33 and 70 kilometers below the surface. The blue dots, 150 to 300 kilometers beneath the surface. And the purple dots show between 500 and 300 kilometers below the surface. And a very few red dots actually show very deep earthquakes that go between 500 and 800 kilometers below the surface. This slide shows how the strength of the crust, or actually the lithosphere, increases as you go down with depth. You can imagine as you go down with depth in the earth, the more and more pressure that occurs in the rocks, the harder they're pushed together and the stronger they are. But eventually, you push hard enough, and remember the temperature increases as you go down the earth, things start to melt. And instead of behaving brittly, they start behaving plastically. Remember how we determine this rheology? We can imagine this rheology. If you deal with something that's brittle, usually in the lithosphere, you hit it with a hammer, it makes a crack. Something that forms more plastically, has a more plastic rheology, you hit it with a hammer, it makes a thud. This is where you stop generating earthquakes. When you increase in strength as you go down through the crust, the rocks go from brittle, where they actually make earthquakes, to more plastic, where the rocks flow and they actually don't crack, so you can't really make earthquakes. This depth we have marked here is 15 kilometers, but it's not always that depth. Start thinking about what could change that depth, what could make it higher and what could make it lower, and that's going to help govern the strength of the earthquakes. Remember, the size of an earthquake is going to be related to how much fault actually ruptures, or how much brittle material there is available to break, and that's going to be based on how deep this brittle ductile transition is, and that's what we'll talk about next time. This is the end of this lecture.